Good morning, everyone. I've just been speaking to Will Gordle, actually, who's in the second row here, ahead of this presentation, and we were talking about this very topic of how we can, in operations today, reduce our emissions through improving efficiency, and that improving efficiency also has a natural cost impact that then drives higher profitability in our existing operations. I think at this conference there's been a lot of talk about the reporting and the data verification and the systems that will enable accountability and governance of energy efficiency going forward. But this presentation's talking more about what we can do today in our operations across the whole mine value chain. So what is, orebody learning? Orebody learning has already been used across the whole mine value chain for a range of different applications, and I'll go through what some of those are shortly. But in this presentation, I'm going to focus specifically on the benefit and the operational improvement in terms of energy efficiency that you can get now. And so it's just an example. We can think of it as what can engineers, across the whole mine value chain, learn from their operational experience, and from that operational experience, how can they reduce their energy consumption? So already, Maxter is being used across the whole mine value chain. We're using it, or our customers are using it, in small gold mines right through to the largest open pit iron ore operations in the Pilbara, running 170 million tonnes per annum. So they've got 19 models. So this is proven technology that's already being used for value chain optimisation. And these are some of the areas across the value chain where we see that this can easily be applied today to improve efficiency in our operations. So have an impact now rather than necessarily just reporting and capturing the data, but to improve things as it is. So in the drill and blast side, most of us here have got a mining background, so you may or may not be aware that blasting is actually a more efficient way to break rock and to affect comminution. And so there's a natural efficiency that if you can bring that comminution forward into the mine, that you can improve your efficiency. So that's one area. The second area is, has anyone been out in an open pit operation and seen the haul trucks over trucking and under trucking? I'm getting quite a few nods around the room. That's a common problem. And the reason that happens is because the dispatch systems often have a bit of a lag when the rock type changes. And what that means is that if they suddenly go into a weaker rock formation, they're going to suddenly get higher dig rates, and then the number of trucks, if it's higher dig rates, then you're going to end up with not enough trucks to be there, so you're under-trucked. But if there's much slower digging conditions and you suddenly hit a hard ore patch, that won't be picked up by the dispatch system's regressions that they use over usually it's about 6 hours or a shift. They'll be getting a regression to predict that dig rate. But if it suddenly changed rock type, then you're going to get this lower dig rate, and then you're suddenly going to be over-trucked. And the trucks are all just sitting there, idling, waiting for to be loaded. So there's an area there. Another thing we can do already is blend optimisation. So a lot of times people think about blending as being about minimising variability, but there's a much more important aspect of blend optimisation, and that is how do you combine your ores to actually get the most efficiency in your comminution circuit. We're already using that approach for other reasons like recovery improvement in the plant and crusher improvement of crushers through blending, but I really would love to see the same approaches of blending being used to improve the efficiency of comminution, especially for your ag mills and your SAG mills. In terms of the grinding, I've already covered that a bit, but that specifically can also be around efficiency through how you operate the SAG mill. I am a mining engineer, so this is not my domain, but my technical director, Jelka, who's a co-author of this presentation, what we do there is we can look through the data and learn from that data which set points achieve the throughput that is required at the grind side that is required. But at some point what happens is they keep adding energy, keep increasing the energy consumption, but you could actually dial it back a bit when you get only a slight reduction in your throughput. So there's a point of diminishing returns in how the mills are being operated, especially if they have a variable speed controller. You can wind them back a little bit and get quite a big improvement in efficiency. So that's the other area in that set point optimization space. And then finally, in the area of crushing as well, and I've already talked about how you can get different, comminution properties through set points in the crushers as well. So as I said before, we're already doing optimization for the purpose of things like throughput and recovery and all the normal operational improvement initiatives that you will see at site. But I just wanted to emphasize that this same approach can be used for improving energy efficiency. So what is orebody learning, you might be wondering at this point, and how does it work? So typically when we are planning our mines as mining engineers, or if we're metallurgists in the plant, we don't get a high level of precision in the characteristics of the ore that's going into the plant, or the granularity of the ore behaviour for drill and blast, for example, or for other planning purposes. So what orebody learning does is it enables you to learn from tens to hundreds of millions of tonnes of operational data that you've been generating at that site per year. And you can continuously update that. So as you get better and you change things in the mine, then the machine learning models that are built into this will continually improve, and you'll get even more uplift through your operations. So as you can see here, we tend to think of we forget to cut our rocks basically in half and just see how complex they are. And it would be great to see some of these specimens, these polished specimens in the lobbies of some of the mining companies like you used to see. You used to see geology specimens. This one, actually, I took this photo at the Natural History Museum in London back in 2019, just because it reminded me of just the level of variability that we are dealing with in the inputs to our processes. And so through orebody learning, we're able to link this information into our improvement in the value chain. So how does it work? The complex part of this is that there's always been a gap between the value chain, all the different areas of the value chain, like your crushers and your mills, because we weren't able to link directly the performance of that asset to the geology. And so Maxter really, it's the core IP in it is actually the ability to track the ore through this value chain. And we do that using a new type of ore tracking. It doesn't require any hardware. It uses data fusion ore tracking, which is built upon machine learning as well. So what are we doing with this ore tracking? We're effectively twinning the geology to all of the processes downstream that you may want to optimise. So sometimes we'll refer to it as digital twin modelling. It's the same, but more and more we're starting to say orebody learning is what Maxter is doing. But you can also think of it as a digital twin model. What can a modern mine learn from this experience from orebody learning and from their experience every day? You can get more accurate predictions for mine planning across all your time horizons. So that includes right from daily right through to life of mine. And we've got case studies on all of that. But in this particular case, that would be for the prediction of specific energy. And I'm going to give you a case study on that in a sec. Best blasting designs, which blast designs give you the best performance, the best plant set points I've talked about, and also the optimal blending. That's a bit of a summary. So a case study now, just to make this seem a little bit more real and tangible. This is an open pit mine in Western Australia, and it's a specific energy machine learning model. We built this model at our own expense to demonstrate this. We've actually done other work at this site related to throughput and optimising of the processing and for predictability and drill and blast. But we wanted to demonstrate, and this case study's actually been accepted and will be published at the Open Pit Operators Conference in June this year. So that is co-authored with people from that operation as well, from the site. That it's based on hundreds of millions of tonnes of ore that's been tracked through that process. So this is a specific energy case study, which we've done at our own initiative. What you can see there on the right-hand side is the specific energy block by block prediction. So with Maxter, what we basically are doing is adding, for every block in the block model, a predicted specific energy based upon all the geological attributes that we have tracked through the value chain. So when we're tracking that all right through, we get all of the block model variables. Typically, there'll be hundreds of them. And then we build that machine learning model so that every block in the block model has its own individual prediction, normally based on between 50 and 100 different block model variables. What that means then is that mine planners when they're doing life of mine optimization, they're able to take that increase in cost that is associated with higher specific energy, higher grinding costs, and include that as a cost in the optimization process. So this naturally feeds into optimizations that are already happening in mining, because we already do optimization, but we don't consider the difference in the energy costs. And so just by doing that, I'll just show you what that does. This is what the software looks like. So basically you upload the block model, and then it just adds all the specific energy predictions as a new variable to the block model. But what the big opportunity here is, in the case of optimization, if you are including that difference in energy costs associated with specific energy more accurately, that means that when you run your optimization, it's going to naturally select blocks that have a lower specific energy than the ones that have a high specific energy, because their cost is higher and therefore they're less profitable on a block by block basis. So in this particular case study, this is what it looked like. We estimated about 1.5 kilowatt hours per tonne energy saving was possible over that deposit. And the reason for that is that the blocks that were of a similar grade, which were lower specific energy, they then become ore, whereas in the past they would have been waste if they had slightly lower grade, because if you just use a grade cutoff, you don't take into account this difference in energy. But conversely, and most importantly, the high specific energy ones, the ones that cost a lot, and this is in an ore body that has very high variability in their hardness, those higher specific energy blocks are then not mined. And that's where you get the energy savings from, because the optimizer is naturally going to select the lower specific energy blocks. Then another area I talked about at the beginning was another opportunity that exists already in operations is drill and blast. This is not a new one. I think most people have heard of mine to mill optimization. It's pretty much the same thing. It's just a way of doing it that's not a consulting business model. It's built into your operations through the software. So it's a way to undertake continuous mine to mill optimization. The case study I'm going to present, unfortunately, is not an energy efficiency one. We haven't done one yet, but it'll illustrate the point. So this is an iron ore case study as well. They have a problem with crusher downtime due to blockages at the crusher. And this case study, again, is going to be presented to open pit operators. And again, the mine site involved is a co-author of that paper too. So what's different with this approach to mine to mill optimization is, if you remember at the beginning, I talked about fusing the geology directly to the downstream process. So in this case here, we've fused through the ore tracking the geology to the problem of crusher downtime. So we link crusher downtime directly to the geology, and we link the drill and blast as well. So the drill and blast design is appended to that ore tracking. So you've got all your drill and blast design variables and all your geology all appended, all tracked right through to the crusher. And then from that ore tracking process, we're able to then build the machine learning model, which is then used to simulate different blast designs. And in this case, you can see they've got two crushers. If you look at each row is a different simulation. Each time they upload a polygon that they want to blast, they can run multiple simulations, changing the blast design levers that you can see along the bottom, so they can change the density, the diameter, the subdrill, the stemming. But what you can see here is when they've changed the density of explosive, they've gotten a different result. If you look at the second last and fourth last columns, you can see that they're getting a different effect on the percentage of blocks that are reporting as having caused a downtime at the crusher. So the first row there, you've got 4% of blocks reporting and causing blockages at the crusher, and in the other crusher, it's, I can't read it from here. 3% there. So the engineer then runs through each of those lines as a different simulation, and they're able to see the impact directly through the machine learning model. So there's no need to measure fragmentation. There's no need to have an empirical model. You actually got your own operating model that you're learning from your own experience. And what this means is that when you have less, it's becoming more and more difficult to get drill and blast engineers across the world, actually, not just in Australia. And so this is a way for the best drill and blast, most experienced drill and blast engineers, their experience will be captured by the machine learning models. And then when they're not there, they're not on site, you've got a junior engineer, they're able to run this type of simulator and see what the effect is on performance. And you can have as many different performance criteria as you like. We have got customers that have up to 4 different criteria on their drill and blast, and they can see them all simultaneously, and they can also see the impact on cost. So we haven't done one of these yet for energy efficiency, but you could see how we'd just be replacing or adding another column there, which would simply be what is the specific energy impact of each of those. And you can also see the cost effect as well. So that's the presentation today on energy efficiency. I did want to leave a little bit of time so you could ask questions. I recognise that this is actually quite a new thing, the orebody learning, and some of you would have heard some of these bits and pieces before. I'd really love to have some questions if we can from the audience. You may have to speak up loudly though to be picked up by the microphone, or I can repeat the question. No. Oh, we've got one there.
Is this all open cut or is it underground as well?
Oh, that's a good question. So far, we are only working in open pit because that's where we can get the fleet management data that we use to track the ore. But we are looking to do it underground as well, and we're part of the ARC Training Centre for Complex Ore Bodies, which is part of the University of Adelaide, and 2 of the other sponsors, PETRA is a sponsor as well, 2 of the other sponsors are underground operations, and that's the reason, one of the reasons we joined that training centre was because we want to see this, the PhD students to apply this in and develop it for underground operations as well. But it's really the lack of, in most underground mines, it's just not the same level of fleet management data that you get from open pit. But I think that is going to be changing soon. We're seeing more and more underground mines starting to get that level of data from their sites.
Would you consider ventilation as an optimisation for energy consumption?
That's a very good point. Would be a very good application actually. So it's not one we've looked at, but that's a big consumer of energy in the underground mines. Good point. So I guess that's a point that you're making then, is anywhere where you can see opportunity in operation to reduce your emissions and improve efficiency is not just an opportunity it's also a cost saving. So it's easy to get the justification. It's more about people knowing that this technology exists. And so that's why we're here today, just to explain that these are things you can already do in operations. Any more questions? Peter?
Is it possible to apply this sort of solution to other metrics like water use or reagent use?
Yes, that's true. So water as well is another area that we believe would be very suitable for, like, how much water consumption for different processes in the plant, and how do you optimise it while keeping your water consumption at an acceptable level. The mines in Chile are really interested in the specific water consumption side of things because there's such a high cost on water. Yep.
And is there a feedback loop? So this will predict and simulate what you're going to do, but what happens about what actually happened? So does that feed back into your model at any point in time?
Look, that's what we're at the moment is in this processing plant. Well, the set point optimization, that data is already collected in the historian, and so you can automatically run a retrain on the model. In the mines, they don't often have that data live, so the FMS data is not always available. If it is live, it's not available for an application to run on. We believe that isn't that far away, but for right now, we actually require the customers to provide that data through our secure Maxter portal uploader, and then that means we can retrain the model. So say they've done a drill and blast trial or something, then a trial of different explosives, and they've done that for a couple of months. They would then upload that trial data, and then we would rebuild the models based on that. That rebuilding process is really, we've almost automated it now. It's probably a couple of weeks from the time we receive the data to the time the new models are deployed. So you might notice I haven't talked about the machine learning as much. That's because we've a lot of that machine learning side of things now is becoming fairly easy to automate through AutoML, and is not the most difficult part of this whole thing. Isn't the machine learning, it's that ore tracking component, which has been a challenge in mining for forever. Yes?
Is there an opportunity to link the models, like take your load and ore model and your specific energy model and take that as a total emissions and the relative contributions? That's sort of the next step.
I think that's a great opportunity. We haven't done that yet with Maxter, but I would, I'd be very interested in linking it into other. There's some other software providers here. We are platform agnostic. We know there are other companies looking at the energy efficiency across the value chain, and we probably wouldn't necessarily add our own application layer for that purpose, but we would take the view to provide the predictions and the data to any application that wants to through APIs, ideally through interoperability, but not many companies have got that, unfortunately. All right, well, that's pretty much on time, and I thank you all for attending today. If you've got any other questions, please feel free to come and have a chat afterwards. Thank you.